So I want you to picture a very specific scenario. It is like 2 o'clock in the morning.
Oh, I already know where this is going.
Right. You've been there. The glow of your monitor is literally the absolute only light in the room. You have this cup of coffee sitting next to your keyboard, and it went completely cold at least, probably 3 hours ago.
Yep, the classic late-night debugging session.
Exactly. And you are staring, just glaring, really, at a block of code on your screen. And specifically, you're staring at a while loop.
It's always a while loop.
Always. You are currently playing the software developer's absolute favorite guessing game. You're looking at a variable, and you're asking yourself, wait, should this termination condition be strictly less than? Or does it need to be less than or equal to?
Oh, man, the classic off-by-one anxiety. It really is a rite of passage for anyone who writes software.
It's just the worst.
It is, because you fix a bug by adding an equal sign, right? But in doing so, you somehow break 3 other test cases that were previously working perfectly fine.
It is the absolute worst feeling, because you get inside the loop, you're updating your pointers or your indices, and you're thinking, does my right boundary equal mid? Or is it like mid minus 1? Or maybe I should add 1.
You just start doubting everything.
Totally.
Yeah.
So you run the code,
Yeah.
and it either crashes with an index out of bounds exception, or honestly, much worse, the terminal just freezes. It hangs forever in an infinite loop.
Oh, the silent hang. Terrifying.
The fan on your laptop just spins up to maximum. Your CPU is basically crying for mercy, and you are reduced to just throwing random +1s and -1s at the logic, just praying that something eventually passes the test suite.
Yeah, we call that programming by permutation.
Programming by permutation. I love that.
Right, because you aren't actually designing an algorithm anymore at that point. You are literally just manually iterating through every possible combination of boundary conditions until the compiler just stops yelling at you.
Yes, and once it finally passes, you just back away from the keyboard slowly.
Exactly, and you just hope nobody ever asks you to explain why that specific combination of boundaries actually worked.
Because you have no idea. Anyone who has ever written or even just tried to read logic in a computer program has felt that exact flavor of pain. But for today's deep dive, we are looking at a stack of notes covering a computer science concept that acts as, well, a complete cure for that pain.
It really is a cure.
And the name of the concept sounds, highly academic. It sounds like something you'd hear in a graduate-level discrete mathematics course, so it could be a little intimidating. It is called the loop invariant.
Yeah, and the notes actually provide the Chinese translation, too, which is shit in in.
Right. But before we even define what that actually is, we need to completely reframe how we think about the concept, don't we?
We do. Because when most developers hear the phrase loop invariant, they immediately assume it is some strict, arcane rule that the computer requires in order to compile the source code.
Like a syntax thing.
Exactly. But the computer absolutely does not care. The machine will happily execute your infinite loop, just allocating memory and burning electricity until the heat death of the universe.
It has no self-preservation instinct.
None. The computer doesn't need an invariant.
So if the computer doesn't care at all, who is this actually for?
The loop invariant is a tool specifically designed to reduce the cognitive load on the programmer's brain. It is a mental framework for human beings, not machines.
Oh, okay, that makes sense.
Because when a loop is running, variables are shifting states thousands or millions of times a second, right? It is this incredibly chaotic, dynamic system. And the human brain is just notoriously terrible at holding the state of a dynamic system in its working memory over time.
Oh, absolutely. We can hold, 7 things in our head at once?
If we're lucky.
Yeah.
So the invariant is a way to stop trying to track everything.
So our mission for this deep dive is to understand exactly how this concept acts as an anchor in your algorithm's logic. I like to think of it as an unbreakable promise.
I like that word, promise.
We're going to look at how it takes all that chaotic, dynamic movement you mentioned and distills it into clear, static, and absolutely foolproof rules.
Yeah, it basically transforms the act of writing a loop from a guessing game into a mathematical certainty. You stop trying to hold the entire timeline of the program in your head. Instead, you design one single, unchanging truth, and you force your code to adhere to it.
Okay, let's unpack this. Let's lay out the anatomy of this promise. Because before we can use this tool to solve complex Leetcode problems or debug a piece of production software, we need to know how a loop invariant is actually constructed.
Right, we need the blueprint.
So according to the notes, the definition is this. A loop invariant is a specific condition or a property of your variables that remains strictly true before and after every single step, like every iteration of a loop.
Yeah, Always true. That is the fundamental philosophy here. No matter how many laps the loop has run, whether you're looking at the state of the program just before the very first iteration, or you're pausing it right after the, I don't know, 10 millionth iteration, this specific condition you defined has never been broken.
And to mathematically guarantee that this condition is always true, the notes lay out a very specific three-step verification process,
Yeah.
like a triad. Step 1 is initialization. Step 2 is maintenance. And step 3 is termination.
And if you have ever studied pure mathematics, you will immediately recognize this architecture.
That sounds super familiar.
Right. What's fascinating here is that it mirrors mathematical induction perfectly. In induction, you prove a statement is true for a base case, like n equals 1.
Right.
Then you prove that if it is true for an arbitrary step k, it absolutely must be true for step k plus 1. Once you establish that domino effect, you can draw a grand conclusion for all possible numbers. The loop invariant is just mathematical induction applied to computer memory.
Okay, I am tracking the domino analogy, but I actually want to map this onto a more physical scenario to make sure I really grasp the mechanics of those three specific steps.
Go for it.
Let's imagine a relay race taking place on an endless circular track. The baton that gets passed from runner to runner is our loop invariant. It is the promise itself.
Okay, I like where this is going.
So, step 1 is initialization. The rule here is that the condition must be true before the very first iteration of the loop even begins. In our race, that means making absolutely sure the very first runner is physically holding the baton in their hand before the starting gun even goes off.
Yes. And if we look at real-world debugging, a failure in initialization is one of the most common sources of catastrophic bugs.
Really, just right at the start.
Oh, yeah, because if your premise is false before the engine even turns over, the entire structure collapses. You have to set your initial variables up in such a way that the invariant is already true at step 0 before any code inside the loop has actually executed.
Right, so if the first runner starts sprinting without the baton, it doesn't matter how fast they run. The race is already disqualified.
Exactly. The race is over before it started.
That makes a lot of sense.
Yeah.
So, assuming the starting runner actually has the baton, we hit step 2, which is maintenance. The rule here states that if the condition is true before an iteration starts, the code executing inside the loop must ensure that the condition remains true the moment that iteration finishes.
It has to maintain the state.
Right. So, back to the track. Runner A starts their lap holding the baton. No matter how tired they are or what weird obstacles are on the track, they must successfully hand that baton to runner B at the exact end of their lap. The baton must remain in play.
Yeah, the maintenance step is where the actual computational work gets done. You assume the promise was kept up to this exact moment. Now, your code inside the loop introduces new information.
Like reading a new file or something.
Yeah, exactly. Maybe it reads a new line from a database or looks at the next element in an array. Your code has to react to that new information, process it, alter the state of your variables, and reestablish the truth of the invariant before the loop loops back around to start the next lap.
So if runner A drops the baton halfway through the lap, the maintenance has failed. The invariant is broken.
Precisely. The promise is dead. And that brings us to the final step, which is termination.
Right. Step 3. When the loop finally ends, when the race is over, we combine our always true condition with a specific reason the loop stopped in the first place. And combining those two things gives us our final answer.
This is the massive payoff of the entire framework. If you initialized the state correctly, and you wrote code that maintained the promise through every single iteration.
Which is the hard part, yeah.
Right, but if you did it, then when the while loop finally breaks, you don't have to guess what state your program is in. You know for a mathematical fact that the invariant is still true, and you know that the termination condition has been met. You smash those two pieces of knowledge together, and your algorithm's correctness is basically proven beyond a shadow of a doubt.
So I want to tie this back to the listener who is pulling their hair out at 2 a.m.
Yeah.
Why does formalizing this relay race matter when you are just trying to fix a stupid bug?
It matters a lot.
Yeah, it matters because when your code throws an error, you shouldn't be randomly tweaking +1s and -1s.
Right.
You should pause your debugger and ask a very specific question. At this exact moment, in this specific iteration, does my variable still satisfy the promise?
Yes. And if the answer is no, you have isolated the bug. The baton was dropped on that exact lap. You no longer have to comprehend the entire massive program. You only have to look at the 3 or 4 lines of code inside the loop body that failed to reestablish the invariant. It drastically narrows the universe of possibilities down to a single point of failure.
That sounds incredibly powerful in theory, but talking about mathematical induction and endless relay races feels, I don't know, highly abstract. The notes suggest we apply this framework to something incredibly basic to see the mechanics in action.
We definitely should.
We need to prove the obvious before we try to tackle anything complex, right?
Let's find the maximum value in an array of numbers. It is literally the simplest algorithmic problem imaginable.
Okay, let's set up a specific scenario for the listener. We have an array called A. And just to make it interesting, let's say the array is full of negative numbers, which often trips up beginners.
Oh, it always does.
So the array A contains the values, -10, -3, -5, and -1. We want to write a loop to find the biggest number.
Right. So the standard intuition here is to declare a variable, let's call it maxval, to hold our answer. Then we loop through the array. If we see a number bigger than whatever is currently inside maxval, we update maxval with the new number.
Simple enough.
And when we reach the end of the array, maxval will hold the correct answer.
That is the intuition, yeah. But we are going to look at this strictly through the lens of our 3-step framework.
Yeah.
What is the loop invariant here? We have to define the promise.
We do.
So the notes define it precisely. The variable maxval always holds the maximum value of the subarray we have looked at so far. To put it mathematically, at any given step I, maxval equals the maximum value found in the array A from index 0 up to index I minus 1.
Okay, let's run that definition through the triad. Step 1, initialization. We need to ensure the promise is true before the loop even starts. What should we set maxval to initially? Because a common beginner mistake is to initialize maxval to 0.
Oh, let's trace that failure, because that's a great point. If we set maxval to 0, we check our invariant before the loop starts.
Right.
The subarray we've looked at is either empty or maybe just the first element. But if we say maxval is 0, and our array only has negative numbers, well, 0 isn't even in the array.
Exactly. The invariant is instantly false. The first runner doesn't have the baton.
It's an immediate fail, which is exactly why initialization is so critical. To satisfy the invariant before the loop starts, we must assign maxval to be the very first element of the array, which is A0. And we will set our loop counter I to start at index 1.
Let's check the invariant now. Before the loop begins, I is 1. The subarray we've looked at so far is just the elements from index 0 up to index 1 minus 1, so just index 0.
Right.
The element there is -10, so maxval is assigned -10. Is maxval the maximum value of the subarray containing just -10? Yes, it is. The promise is true. Initialization is complete.
Okay, step 2, maintenance. We assume the promise has been kept up to the current iteration. Maxval holds the biggest number we've seen so far. Now, our loop counter I moves forward, and we look at the new element, AI. In our array, that's index 1, which holds the value -3.
So our loop body has to react to this new information, it asks. Is -3 strictly greater than our current maxval, which is -10?
It is. -3 is a larger number.
Right. So the code updates maxval to be -3. And the iteration finishes.
Pause the program right there. End of the first lap. What is the state of the universe? Our loop counter I is about to increment to 2. The subarray we have examined is now index 0 and index 1, so -10 and -3. Does maxval, which is now -3, accurately reflect the absolute maximum value of that specific subarray?
It absolutely does. The promise was maintained. We reacted to new data, changed our state, and reestablished the truth.
The baton was passed successfully.
Exactly. And we would do that exact same process for the -5, where maxval wouldn't change, right?
Because -5 is smaller than -3.
Right. And then for the -1, where it would update again, the baton never drops.
Which brings us to step 3, termination. The race ends. What is the specific reason our loop stops running?
Well, the loop terminates when our index I reaches the total length of the array. Let's say the array length is n, so the loop stops when I equals n.
Now, execute the final logical step. Combine the termination condition with the loop invariant. Our invariant states that maxval always holds the maximum value of the array from index 0 up to index I minus 1.
Yep.
And our termination condition states that I now equals n.
So if you substitute n into the invariant, maxval holds the maximum value of the array from index 0 up to index n minus 1.
But index 0 to n minus 1 is literally the entire array.
Exactly. Therefore, maximal must hold the maximum value of the entire array. The algorithm is proven correct.
I completely see how the logic locks together. It is very satisfying. But I have to push back here because I know exactly what you, the listener, might be thinking right now.
Oh, I bet I know too.
Yeah, I could write a find the maximum value loop in my sleep, right? Like while heavily medicated. I do not need to define a formal invariant and walk through a three-step mathematical induction proof just to find the biggest number in a stupid list. Isn't this massively overcomplicating a trivial problem?
You know, you make a fair point. Applying strict mathematical induction to a simple linear scan is akin to using a sledgehammer to crack a peanut.
Exactly.
But here's the thing. You do not practice new mental frameworks on the most difficult problems first. You practice them on trivial problems so the mechanics of the framework become second nature. Because while you can find a maximum value in your sleep, can you sit down right now with no references and write a completely flawless binary search algorithm on the first try?
Oof. No. Honestly, no. That is exactly where I usually find myself throwing those plus ones and minus ones at the while loop that we talked about earlier.
Most people can't.
The core concept of binary search makes total sense to me. You check the middle, and if it's not what you want, you chop the array in half. But the boundaries always trip me up. Always.
That is the universal experience. The notes actually refer to this exact phenomenon as boundary hell.
Boundary hell, that is the perfect name for it.
Right. Complex algorithms like binary search, sliding windows, or two-dimensional dynamic programming, they almost never fail because the developer doesn't understand the core idea. They fail because the boundaries get sloppy. Building the mental framework of the loop invariant is the ultimate weapon against boundary hell.
Okay, let's trace binary search as an example then, because the notes highlight it specifically. You're searching for a target number in a sorted array. You have a left pointer starting at index 0 and a right pointer starting at the end of the array.
So in binary search, your invariant defines the search space. Your promise might be, if the target exists anywhere in this entire array, it is absolutely definitively located within the closed interval from the left pointer to the right pointer.
Let me make sure I understand closed interval. That means the target could potentially be sitting exactly at the left index or exactly at the right index or obviously anywhere in between. The boundaries are inclusive.
Correct. Both ends are inclusive. That is your initialized promise. Now, inside the loop, you calculate your mid-index and you check the element there. Let's say the element at mid is too small. It's not the target. You need to chop the left half of the array away.
Right.
Here's where the boundary hell usually starts. Do you set your new left boundary to equal mid, or do you set it to mid plus 1?
Okay, if I rely on the invariant, my promise is that the target is strictly inside the closed interval left-right. I just checked the element at mid, and I mathematically confirmed it is not the target.
Yep.
If I were to update my boundary by setting left equals mid, my new closed interval would include that mid-index.
Yeah.
I would be including an element that I already know is useless.
Yeah.
That violates the tightness of my invariant, right?
It does more than that. It creates a potential infinite loop.
Wait, really?
Yeah. If your left and right pointers are right next to each other, like indices 4 and 5, and you calculate mid as 4, and then you set left equals mid, well, left stays at 4, the pointers might never cross, and the loop hangs forever.
Oh, wow. I've definitely done that.
We all have. To maintain the invariant that the target is within the boundaries, and to ensure the search space is strictly shrinking, you must set the new left boundary to mid plus 1. You know mid isn't the target, so you safely exclude it.
That changes the perspective entirely, because it's not a guess, it's a rule.
Yeah.
But what if I decided to write my algorithm differently? What if I initialized my right pointer, not to the last index, but to the length of the array itself, like an index that is technically out of bounds?
If you do that, you have changed your invariant.
Okay.
Your promise is no longer a closed interval. It is now a left closed, right open interval, meaning the target could be at left, but it will strictly never be at right. The right pointer is an exclusive boundary.
So if my invariant is a right open interval, and I check mid and it's too big, so I need to chop the right half away, how do I update the right pointer? I know mid is not the target. My invariant says the right boundary is exclusive. It's an index I know the target is not at. So setting right equals mid becomes the mathematically correct move.
Exactly, because mid is now the exclusive boundary.
Because I don't want to include mid in my search space anymore, and the right pointer is designed to be excluded anyway.
You see how the math forces your hand? If you define your invariant clearly before you write a single line of logic, you never have to memorize a dozen different binary search templates. The code practically writes itself. The rule dictates the boundary updates.
That is a massive paradigm shift. It completely removes the guessing game. I love that. So we've seen how the framework works and how it handles boundaries. Now, the notes suggest we look at how the maintenance step of an invariant can actually replace complex mathematical operations. It introduces an example using Leetcode problem 171.
This is the Excel sheet column number problem. It is a fantastic illustration of using an invariant to accumulate value dynamically.
Okay, I'll lay out the premise for the listener. The problem asks you to convert an Excel column title into a corresponding number. So column A is 1, column B is 2. This goes all the way up to column Z, which is 26.
Makes sense so far.
But then the alphabet runs out, so Excel rolls over. The next column is A, which is 27. AB is 28, and so on.
Fundamentally, this is a base conversion problem. We are trying to convert a string written in base 26 into a standard base 10 integer. But there is a very nasty, insidious twist to this problem. It lacks a 0.
Wait, let me see if I have this straight. In our standard base 10 number system, we have 10 digits, 0 through 9. In this Excel system, we have 26 characters, A through Z. But A represents 1. Z represents 26. There is literally no character that represents the concept of 0.
Correct.
Why does the lack of a 0 make this so difficult?
Because it completely shatters standard modulo base conversion algorithms. Let's trace a failure to see why. Suppose you wanted to do the reverse convert the number 26 into an Excel column. In standard base conversion, you use the modulo operator to find the remainder. If you take 26 modulo 26, the remainder is 0.
Right, it defines perfectly. No remainder.
But what character do you map that 0 to? You don't have one. You only have characters for 1 through 26. The standard mathematical algorithm expects a 0 to exist in your base system. When it doesn't, the math breaks down, and you end up with off-by-1 errors cascading through your place values.
That is so annoying. So to solve this without getting tangled in broken modulo math, we use a loop invariant. We're going to iterate through the string of letters from left to right, one character at a time. The notes define our invariant as this. Before processing the ith character, our variable result stores the exact decimal value of the prefix string we have seen so far.
That's right. Keep that anchor in mind. Result always equals the complete value of the prefix.
The sources offer a really compelling base 10 analogy to explain how we maintain this invariant, and I want to trace it carefully because it makes the underlying math click instantly.
It's a great analogy.
Let's forget base 26 in Excel for a second. Think about how your brain reads a normal everyday number. Let's say the number is 345.
Our brains process that entire shape instantaneously, but if you break it down into a computational process, you read it step by step, left to right.
Exactly. First, you see the 3. At that exact moment, the value in your head is just 3. Then, your eyes move, and you read the 4. Now, that original 3 isn't just a 3 anymore. Because a new digit arrived on the right, the 3 shifts over. Its place value gets elevated.
Right.
It is no longer in the ones place. It's in the tens place. It becomes a 30. Then you add the new digit, the forefront, and your running total becomes 34.
And the process repeats. You see the 5, that 34 gets shifted over again. It gets multiplied by your base, which is 10. So the 34 becomes 340. Then you add the new digit, the 5, giving you the final total of 345. Every single time a new character arrives, everything you have accumulated so far gets multiplied by the base to make room for the new digit.
That mechanism shifting the accumulated total to make room for the new arrival is exactly how we maintain the invariant for the Excel problem. We are just applying it to base 26 instead of base 10. When a new character arrives in our loop, all the previous characters we have processed, which are safely stored in our result variable, need their place value elevated.
Precisely. But instead of multiplying by 10, we elevate them by a factor of 26.
This makes the maintenance formula beautiful in its simplicity. Inside your loop, your code only has to do one thing. New result equals the old result multiplied by 26 plus the integer value of the current digit.
What fascinates me about this approach is what we aren't doing. We completely bypass doing any scary exponential math. I know a lot of developers, when faced with base conversion, immediately reach for power functions. They look at a string like ZYX and try to calculate, okay, the Z is 3 places from the right, so its value is 26 times 26 to the power of 2.
Yeah, they want to use math.pow or write a separate exponentiation function.
But from a systems and computer science perspective, relying on math.pow for integer conversion is a terrible idea. It often deals with floating point numbers under the hood, which can introduce precision errors. It is computationally expensive. It is significantly slower than simple multiplication.
Oh, interesting.
Yeah. By relying on our loop invariant, we are utilizing an ancient algorithm known as Horner's method, or, as it is known historically in Chinese mathematics, Horner.
Horner's method. I've heard the name, but I never connected it to base conversion.
It was originally designed as an incredibly elegant way to evaluate complex polynomials without ever needing to calculate high powers. By simply multiplying the accumulated result by the variable and adding the next constant term, you achieve the exact same mathematical outcome as exponentiation.
But just way more efficiently.
Exactly. It's computationally cheap, it stays entirely within integer math, and it is fundamentally less prone to errors. You are building the exponent implicitly through the iterations of the loop.
Let's prove that this actually works. Let's force a step-by-step trace using Horner's method on a specific Excel string. Let's trace the string CRAB.
Sounds fun.
Now we need the integer values for those letters. A is 1, B is 2, C is 3.
I'll need your help with R, though.
Let's see. R is the 18th letter of the alphabet.
Thank you. So C is 3, R is 18, A is 1, B is 2. We're going to run the triad on the string CRAB. Step 1, initialization. Before the loop starts, we haven't read any characters yet. The prefix we have seen is empty. We initialize our result variable to 0. Is the invariant true? Yes, the value of an empty string is 0. The baton is in hand.
Step 2, maintenance. We begin iteration 1. The first character arrives. It is C, which has a value of 3. We apply our Horner's formula. Result equals our old result, which is 0 multiplied by 26. 0 times 26 is 0, plus the current digit, which is 3. So our new result is 3.
Right.
We pause and check the invariant. Does the result accurately represent the decimal value of the prefix we've seen? The prefix is just the letter C. The value of C is 3. The invariant holds. Iteration 2. The next character arrives. It is R, which has a value of 18. We play the formula again. Result equals our old result, which is 3 multiplied by 26. Okay, 3 times 26 is 78. Then we add the current digit, which is 18. 78 plus 18 is 96. Our result is now 96.
Let's check the invariant. The prefix we have seen is CR. Does CR equal 96? Well, C is the 26's place, so 3 times 26 is 78. R is the 1's place, so 18. 78 plus 18 is 96. The invariant holds.
Iteration 3. The A arrives. Value is 1. Formula old result, which is 96 times 26. 96 times 26 is 2496, plus the current digit, which is 1, so 2497. The result is 2497. The prefix is CRA. The invariant still holds.
Final iteration. The B arrives. Value is 2. Formula old result 2497 times 26. I'm going to trust the math here and just say 2497 times 26 is 64,922, plus the current digit, which is 2. Our final result is 64,924.
And that brings us to step 3, termination. The string ends. There are no more characters to process. The loop terminates. We combine our invariant, which states that result is the absolute decimal value of the prefix seen so far, with our termination condition, which states that the prefix is now the entire string crab.
What do you mean?
Therefore, result, which is 64,924, must be the mathematically exact decimal value of the entire string. We return it, and the problem is completely solved.
It is airtight. And noticing how Horner's method handles the place values is almost magical. By multiplying the running total by 26 sequentially, that initial C got multiplied by 26 3 separate times before the loop ended, which means mathematically it was multiplied by 26 to the power of 3.
Oh, wow.
Yeah, the invariant naturally scaled the place value of every single character perfectly just by repeatedly applying one simple multiplication rule. You never had to actually calculate 26 to the power of 3. The loop iterations did the exponentiation for you organically.
That is just so cool. Okay, strings and arrays are great, but they share a common trait. They rely on contiguous memory. In an array or a string, index 2 is sitting physically right next to index 1 in the computer's RAM. You can just grab the next element.
Right.
But what happens when our data is fragmented? What happens when memory is scattered all over the RAM, connected only by pointers? Let's move away from contiguous structures and look at how invariants work with linked lists.
Ah, linked lists, the absolute bane of many technical interviews.
Truly. The notes highlight Leetcode problem 876, finding the middle of a linked list.
Yeah.
Now, the classic, heavily memorized way to solve this is using a fast pointer and a slow pointer.
Yes, often called the tortoise in the hare algorithm. The setup is simple. You create 2 pointers, both starting at the head or the very first node of a linked list. The slow pointer moves forward 1 node at a time. The fast pointer moves forward 2 nodes at a time.
Okay.
The logic dictates that when the fast pointer reaches the end of the list, the slow pointer will be sitting exactly in the middle.
That is how everyone memorizes the solution. Fast moves twice as fast, so slow must be halfway when fast finishes. It sounds intuitive. But if we want to truly understand why it works and stop guessing whether our while loop condition should be while fast, null, or while fast.next, null.
Which is another form of boundary hell.
Exactly. To avoid that, we need to stop relying on intuition and define the loop invariant.
In this scenario, we do not care about what data or values are stored inside the nodes. We care purely about physical distance traversed across the graph. We define our invariant geometrically. The promise is this. At the start of every single iteration, the total distance the fast pointer has traveled from the start is always exactly twice the distance the slow pointer has traveled.
So the mathematical formula is strictly distance fast equals 2 times slow. Let's run the triad on this physical relationship to prove it.
Let's do it.
Step 1, initialization. Before the loop begins, both pointers are sitting at the head node. They have not moved a single step. So distance fast is 0 and distance slow is 0. Does 0 equal 2 times 0? Yes, the invariant holds.
Now for the maintenance step. Inside the loop, the slow pointer takes 1 step forward. The fast pointer takes 2 steps forward. We need to mathematically prove the ratio still holds after this movement. Let's define the old slow distance as d-slow and the old fast distance as d-fast.
Let me trace the algebra here. If the slow pointer takes 1 step, the new slow distance is d-slow plus 1. If the fast pointer takes 2 steps, the new fast distance is d-fast plus 2. Our invariant demands that the new fast distance must equal 2 times the new slow distance.
Right.
Let's check it. Is d-fast plus 2 equal to, let's see, 2 multiplied by the quantity, d-slow plus 1. If I distribute the 2 on the right side, I get 2 times d-slow plus 2.
Exactly. And remember our initial assumption for the maintenance step? We assumed the invariant was true before the step, meaning we already know that d-fast is equal to 2 times d-slow.
So I can substitute that back into the equation. If 2 times d-slow is just d-fast, then the right side of my equation simplifies to d-fast plus 2, which perfectly matches the left side. d-fast plus 2 equals d-fast plus 2. The math balances perfectly.
It does. No matter how many steps they take, the 2-to-1 ratio is strictly maintained by the mechanics of the loop. The ratio holds. It is undeniable.
Okay, the ratio is undeniably true. But I am going to play devil's advocate for a moment.
Please do.
How does that abstract mathematical ratio actually guarantee that I land on the exact correct middle node when the loop ends? Because finding the middle of a list with an odd number of nodes feels conceptually different than finding the middle of an even number of nodes. There isn't a single middle in an even list.
That is the crucial question, and it brings us perfectly to the termination step. The termination step is where the abstract magic of the invariant hits the hard boundaries of the data structure. Let's assume the total number of nodes in the linked list is a variable we'll call L. And let's break this down into 2 distinct scenarios. Case A is a list with an odd length, and case B is a list with an even length.
Okay, let's trace case A first. An odd length list. Let's say L equals 5. A linked list with 5 nodes. We can think of their indices as 0, 1, 2, 3, and 4.
If the list has 5 nodes, trace the fast pointer. It takes jumps of 2, index 0 to 2 to 4. When it lands on index 4, which is the very last node, it looks ahead. It cannot take another jump of 2 because there is no more track left. The next pointer is null.
Right.
So the loop terminates with fast sitting exactly on the 5th node.
Okay.
Yeah.
Since we started at index 0, stopping on the 5th node means fast has traveled a distance of exactly L minus 1 steps. In our case, 5 minus 1 means fast traveled 4 steps.
Now we apply the invariant. The invariant states that distance slow must be exactly half of distance fast. So the distance slow traveled must be 4 divided by 2, which equals 2 steps.
If the slow pointer starts at the head, index 0, and takes 2 steps forward, it lands precisely on index 2. Let's look at our 5 nodes. Index 0, 1, 2, 3, 4. Index 2 is the absolute perfect geometric middle. 2 nodes on the left, 2 nodes on the right. The math proves it flawlessly.
Now let's trace case B, the even length list. Let's say L equals 4, a list with 4 nodes, indices 0, 1, 2, and 3. In problems with even length lists, Leetcode and typical interviewers usually ask you to return the second middle node. So out of 4 nodes, they want node index 2.
Okay, let's trace the fast pointer on a length of 4. Jumps of 2, starts at 0, jumps to 2, jumps to 4. Wait, there is no index 4.
Exactly.
So it completely falls off the end of the list and lands on null. To fall completely off a list of length L, it means the fast pointer has traversed exactly L steps.
Correct. The distance fast traveled is exactly 4 steps. Now apply the invariant again. Distance slow must be half of distance fast. So 4 divided by 2 equals 2 steps.
And once again, starting from the head and taking 2 steps puts the slow pointer at index 2. In a list of 4 nodes, 0, 1, 2, 3, index 2 is indeed the second middle node, exactly what the problem demands.
Yep.
We didn't have to write messy if statements checking for odd or even lengths. The mathematical ratio naturally resolved both cases just by defining what the end meant for the fast pointer.
When you connect this to the bigger picture of algorithm design, this mental model of tracking distances is vastly superior to just memorizing while fast and fast.next, because it fundamentally changes how your brain views the problem. It transforms finding the middle into a more simpler, robust task. Finding half the end.
Finding half the end. I really like that framing.
You define where the end is, whether it's stopping on the last node or falling off completely, and the invariant mathematically guarantees the slow pointer will be exactly at the halfway mark.
And the beauty is, once you view pointers as a ratio of distances, you can adapt this logic to solve any variation of the problem effortlessly. What if an interviewer throws a curveball and asks you to find the kth node from the end of a linked list?
You don't panic, you don't try to memorize a new template, you just change the invariant. Instead of a 2-to-1 ratio, you decide to maintain a strict, fixed gap between the pointers. Your new invariant becomes the distance between the fast pointer and the slow pointer is always exactly k.
So to initialize that, you just move the fast pointer forward k times while keeping the slow pointer completely still at the head. Now the physical gap between them is exactly k. Initialization is complete.
Exactly.
Then for the maintenance step, you just move both pointers forward one step at a time at the exact same speed. The gap remains strictly k.
And for termination, when the fast pointer falls off the end of a list and hits null, where must the slow pointer be? Because the gap was strictly maintained at k through every single iteration, the slow pointer is mathematically guaranteed to be exactly k nodes away from the end. It's the exact same framework, you are just enforcing a different promise.
This is why senior engineers always hammer on mastering the fundamentals instead of memorizing code. The invariant is the fundamental truth underneath all the pointer manipulation. All right, let's take a deep breath. We have covered arrays, we've explored Horner's method with strings, and we've navigated moving pointers based on distances. I want to tackle one final scenario from the notes.
This is the most complex one in the documentation.
It is. In our fast and slow pointer example, both pointers were constantly moving forward, just at different speeds or with a fixed gap. But what happens when an invariant demands that a pointer stay completely, stubbornly still? What happens when moving a pointer forward would actively violate the promise and corrupt your data?
Now we are venturing into Leetcode problem 82. Remove duplicates from sorted list 2. This is a notorious problem. It is a filter that trips up countless intermediate developers during interviews because the edge cases feel overwhelming.
I'll describe this scenario. You are given a sorted linked list, but some of the numbers in this list are duplicated, and the strict rule for this specific problem is you must remove all instances of a duplicate. You cannot just leave one of them behind.
Right, total eradication.
You must eradicate the number entirely from the final list. So if you see a sequence like 2 arrow, 3 arrow, 3 arrow, 3 arrow, 4, you must delete all of the 3s. The final list would just be 2 arrow, 4. 0 3s are allowed to survive.
The immediate logistical problem here is the head node. What if the very first node in the list is a duplicate and needs to be deleted? If you delete the head, you lose your reference to the start of the list.
Oh, that's a nightmare.
So the standard architectural setup for this involves creating a dummy node, sometimes called a sentinel node, and placing it in memory right before the original head of the list. That dummy node becomes the permanent, unmoving start of our answer.
And to traverse and filter this list, we are going to use 2 pointers. One pointer is going to be called pre, short for previous. We initialize pre to point at our dummy node. The other pointer is cur, short for current, which we initialize to point at the original head of the list.
Here is where the loop invariant becomes an absolute lifesaver. Without an invariant, trying to manage these 2 pointers while deleting nodes will quickly devolve into a tangled, unreadable mess of nested if and else statements.
I've seen that code. It's not pretty.
It never is. The invariant we must define and protect is this. The path, starting from the dummy node, moving forward up to and strictly including the pre-pointer, only contains nodes that are 100% mathematically confirmed to be completely unique.
Let me repeat that because the wording is so critical. The path ending at the pre-pointer is 100% confirmed unique. It represents the absolute end of the clean, safe, verified list.
Yes, that is the promise.
When I was studying the notes on this, I had to come up with an analogy to help me visualize the pointer movement. I modeled it like a military exploration mission. The pre-pointer is the commander.
Okay, I'm listening.
The commander's single job is to guard the safe zone. The commander will only ever step onto ground that has been completely cleared of danger. The cur pointer, on the other hand, is the scout. The scout's job is to walk out ahead into the unknown territory, the minefield, and check the ground for danger. And in the context of this algorithm, danger means duplicate numbers.
I think that is a highly accurate and useful way to model the roles. The commander's entire purpose is to protect the integrity of the invariant. The scout's purpose is to gather the real-world information necessary to eventually update that invariant.
So let's trace the maintenance step in detail, because this is where developers write the bugs. Let's trace a complex minefield. The scout, cur, walks forward and encounters a conflict. The scout looks at the ground they are standing on and sees the number 3. Then the scout looks ahead at the next node, cur.next, and sees another 3 foot. The values match. Danger has been detected. The scout has entered a minefield of duplicates.
So what does the algorithm dictate the scout must do? The scout has to navigate the entire length of the minefield. We implement an inner while loop that simply moves the cur pointer forward, skipping over every single 3 foot it finds until it finally lands on the very last 3 foot in that contiguous block.
Okay, so the scout has run all the way to the end of the 3s. Now, the algorithm needs to update the commander's radio link. We take the commander's node, pre, and we update its next pointer. We set pre.next to point to cur.next.
Essentially, we're taking the commander's chain and throwing it completely over the entire minefield of 3s, connecting it to whatever number comes directly after the last 3.
Right. Let's say the next number is a 4. So now the commander's list points directly to the 4. The 3s have been bypassed and will eventually be destroyed by the garbage collector.
And here is the critical moment, the precise moment where logic usually fails.
It's the pushback I had when I first read the solution. I thought, wait, we just successfully connected the commander's safe list to the 4. The 3s are gone. Why doesn't the commander, the pre-pointer, take a step forward and stand on the 4?
And the answer to that question relies entirely on the loop invariant. Ask yourself, what is the exact wording of the promise?
The promise is that the commander only stands on nodes that are 100% confirmed unique.
Exactly. Now look at that 4. Is that 4 confirmed to be mathematically unique?
No, it isn't. Because the scout hasn't looked past it yet. The scout is still standing back on the last 3. The scout hasn't checked what comes after the 4. There could easily be another 4 right behind it. That 4 could be the start of a brand new minefield.
Therefore, if you write the code pre equals pre.next, instructing the commander to step onto the 4, you have actively violated the invariant. You've placed the commander on unverified ground.
Oh, wow.
If the next node is indeed another 4, your safe zone is now corrupted with a duplicate. The commander must stay perfectly still. The commander must remain on the last known safe node, maintaining the promise that everything behind them is 100% clean. They hold the line, and they wait for the next iteration of the outer loop where the scout will step onto that 4 and determine if it is actually safe.
That clicks so profoundly. It is not a bug that pre doesn't move. It is a strict mathematical requirement of the logic. So what does the logic look like when the ground is safe? Let's trace the alternative scenario. The safe, distinct path.
In this scenario, the scout, cur, is standing on a number, let's say a 5 foot. The scout looks ahead at cur.next and sees a 6 foot. The values do not match.
So the scout radios back to the commander. The 5 is unique. The ground is safe.
Only then, because the 5 has been mathematically confirmed as unique by checking the node ahead of it, is the commander allowed to move. The action pre equals pre.next is finally executed. The commander steps onto the 5. The safe zone has officially expanded by 1 node. The invariant has been successfully, rigorously maintained.
It really is a brilliant mechanism. The commander holding the ultimate truth, the scout exploring the chaos of the data. To highlight why this specific invariant is necessary, the sources briefly contrast this problem with a much easier version. Leetcode problem 83. In problem 83, you still remove duplicates, but the rule is different. You must leave exactly 1 instance of every number. You keep 1 duplicate.
The dynamic in Leetcode 83 is entirely different because the required invariant is different. In 83, the promise is simply, the node the scout is currently standing on is always allowed to be part of the final answer.
Wait, really?
Yeah, because even if the scout steps onto the very first 3 in a block of 100 3s, the rules say you are allowed to keep that first 3.
Which means the scout is never actually in danger. The scout is always standing on safe ground, because the first instance is always valid.
Yeah.
So you don't even need a commander. You don't need a dummy node to protect the start of the list. You just need 1 single pointer that cheerfully walks forward, knowing it's safe, and just severs ties with the redundant duplicates ahead of it.
Exactly. In Leetcode 82, the entire contiguous block of duplicates is considered toxic and must be bypassed, which requires the commander to hold back. In Leetcode 83, the duplicates are just redundant, not toxic. Understanding the profound difference in the required invariant makes the difference in the pointer logic crystal clear. You aren't just memorizing blocks of code, you are understanding the fundamental constraints of the problem space.
We have covered an immense amount of ground today. Let's summarize the journey we've taken. We started with the very real, universal pain of writing a loop, fighting with boundaries, and programming by permutation.
And the 2 a.m. cold coffee.
Can't forget the cold coffee. We introduced the loop invariant not as a strict instruction for the compiler, but as a framework for human relief, a mental anchor to stop the guessing game. We walked through the triad of initialization, maintenance, and termination, seeing how it mirrors mathematical induction.
We saw how that triad effortlessly proved the correctness of a simple max array algorithm, and how that exact same framework scales up to prevent the boundary hell of binary search, dictating exactly when a boundary should be inclusive or exclusive.
Then we leveled up our application. We used an invariant to execute Horner's method in Leetcode 171, converting Excel strings into base 10 numbers without relying on expensive, error-prone exponential math, just through the pure, elegant accumulation of place value.
We transitioned from contiguous memory to the fragmented geometry of linked lists, using an invariant of pure physical distance, a strict 2-to-1 ratio, to perfectly locate the middle of a list in Leetcode 876, proving algebraically why it resolves both even and odd lengths naturally.
And finally, we faced the commander and the scout in Leetcode 82, using an invariant to forcefully hold a pointer back, protecting the absolute integrity of a safe zone while a scout navigated a toxic minefield of duplicates. The overarching theme of all these examples is incredibly profound. Loop invariants are how developers transform dynamic runtime chaos into static mathematical truth.
It is about bringing true rigor to the art of programming. It elevates coding from a trial and error process into an engineering discipline.
It truly does. But before we sign off, the sources left us with one final, incredibly provocative thought to chew on. We spent a significant amount of time on Leetcode 171, where we turned an Excel string into a number by accumulating value left to right. But what happens when you have to perform the exact reverse operation?
Leetcode 168, Excel sheet column title. You are given the integer, say, the number 28, and your algorithm has to build the string AB.
On the surface, it sounds like it should be a standard modulo arithmetic. You keep dividing the number by 26, taking the remainder, mapping that remainder to a letter, and building the string from right to left. Remember the insidious twists we discussed earlier. There is no 0 in base 26 Excel.
That was 0.
A standard modulo operation absolutely expects a 0 to exist when a number is perfectly divisible by the base. If you try to modulo 26 by 26, the math gives you a 0, but we don't have a letter for 0 to put in our string.
The standard algorithm completely breaks down. It will give you the wrong letters, and the string will be too long.
It does. So the challenge I want to leave you with, the listener, as you stare at your monitor tonight, is this. How would you design a loop invariant for that specific problem? If you were building an Excel string from right to left, pulling one character out of the integers at a time, what is the unbreakable promise you need to make to ensure that the lack of a 0 doesn't corrupt your algorithm?
It requires a very subtle, almost counterintuitive adjustment to the math before every single iteration of the loop begins. It is a fantastic puzzle that really tests your grasp of the framework.
It really is. I encourage you to grab a physical piece of paper, write down the 3 steps: initialization, maintenance, termination, and try drawing out the invariant for that reverse problem. Don't start by opening your IDE. Don't start by writing code. Start by writing the promise.
Define the truth and let the invariant write the code for you.
That is perfect advice to end on. That is all for today's deep dive into the loop invariant. We will see you next time.